All right. So, thus far in our study of Chapter 5, we've been following the progress of a certain kind of reaction. A certain kind of reaction. And this reaction is the AB, some chemical AB, which is an ionic aqueous compound, combining with CD, which is an ionic aqueous compound. And I don't know if you've noticed, but when we do this, these are aqueous compounds. That's the cation, that's the anion, cation, anion. Then they just trade places. A goes with D, and usually one of these is solid, and the other one is C going with B, and that usually that one is aqueous, right? And so we have this trading of ions. And remember that we can rewrite it so that we have an ionic equation, B minus plus C plus D minus. And the product is AD plus C, it's a cation, and B is an anion, right? So we have this general formula for chemical reaction, and this is called metathesis reaction, or metathesis. Sometimes people call metathesis, or a double replacement reaction. All right, so in this double replacement reaction, you get ionic compounds that are dissolved in water trading places with each other in terms of the cation from one compound going with the anion of the other. Now, if the product, and I didn't put the solid here to emphasize there, but if the product, or if the new combination doesn't actually create something different than what you start with, then a reaction won't occur. All right, so simply because you put two chemicals in the same container together doesn't mean that a reaction has actually occurred, right? So a reaction will only exist if a precipitate forms, like in this case, BaSO4. Do you know what BaSO4 is, what the name of that compound is?
Barium sulfate.
Barium sulfate. Very good, barium sulfate. So in the case of this reaction, sodium sulfate and barium chloride, both aqueous, trading partners. See how the sodium goes with the chloride and the barium goes with the sulfate. And the product is barium sulfate. And a reaction does occur, we say, because there's a change. The barium sulfate is a solid. It's no longer aqueous as our reactants were. Another way for a reaction to occur is if an acid, HCl, combines with a base, NaOH, hydrochloric acid, sodium hydroxide. Because when they combine, the H here goes with the OH and produces what? What happens if I combine the H plus ion with the hydroxide ion?
H2O.
That's right, water. And that is a liquid. It's not going to dissociate. And so that is also a form of chemical reaction that will occur. You can also have scenarios where a weak electrolyte product is formed from a strong electrolyte reactant. And that's usually like a weak acid, right? And then you also can get scenarios where a gas forms. A gas forms in the product. We don't talk a lot about these last two. You'll see them every once in a while, and more so in homework problems. But this double replacement reaction, right, has our cations changing partners. And let me see, I need to do one thing here. All right, so so what we can do then is for our chemical reaction, if we're given a chemical reaction, just reactants, for example. All right, so what we can do then is we can predict whether or not a reaction will actually occur by looking and seeing if the combination of these reactants will either form a solid or create water from an acid-base reaction. Okay, so remember, it's the solubility rules that helps us know whether or not a product will be soluble or not, right? So we can use the solubility rules to see whether or not we think that a solid will form. And a reaction where a solid forms is called a precipitation reaction. Precipitation reaction. So let's practice again our solubility rules and predict whether or not we think these compounds are going to be soluble in water. What do you think? Is this first one going to be soluble? Calcium acetate.
Oh, found it. Number 2. All salts containing NH4, NO3, C10, ClO4, ClO3, C2H2O2, or 3, H3.
Are what?
Soluble.
Very good. So that means this first one is going to be soluble. How about our next one? Iron 2 carbonate.
Number 6. All salts that contain phosphate, carbonate, and sulfate, and S2 are insoluble.
Insoluble. Very good. So, carbonate, insoluble. Excellent. How about the last one there?
Ooh, number 3. All chlorides, bromides, and iodides, salts containing chlorine, bromine, or iodine are soluble except when combined with Ag, lead, silver lead, and
Mercury.
So unsoluble.
Insoluble. Very good. Excellent. So you remember how to use the solubility rules. Now, look at the products for this reaction and predict whether a reaction will occur or not.
Yes, there is going to be a reaction.
How do you know?
Because it's...
What are the products going to be? Tell me what the products are first.
Lead, nitrate.
Well, that's the reactant, lead nitrate. Very good. And the other reactant is calcium hydroxide. But what are the products going to be?
Oh, it's going to be OH, PB,
All right.
PBOH.
PBOH, lead. What is the OH ion?
Hydroxide.
Very good. So lead hydroxide. And what's the other product?
Calcium nitrate.
Very good. Calcium nitrate and lead hydroxide. Now, are either of those going to be a precipitate?
Yes.
Which one?
It's gonna be Ca nitrate. calcium nitrate.
Is going to be a precipitate?
Yeah.
What rule do you have to show you that?
Number 2, all salts containing NO3 are soluble.
All right, so that's not a precipitate. A precipitate is when it's solid, right? So calcium nitrate is not going to be a precipitate. All right, so what about the other one? Is the other one going to be a precipitate?
Oh, yes, it is. Number 5.
All right, very good. Number 5 said that hydroxides are precipitates with a few exceptions, but lead is not one of them. So we see our products, and remember that you need 2 hydroxides for every lead 2. This is lead 2, we could tell because we had 2 nitrates, and 2 nitrates for every calcium. So there are our products, and lead hydroxide is a solid, showing us that this is a precipitation reaction. Very good. How about this one? Is this one going to create a chemical reaction? And what are the products? What are the names of the products?
Barium chloride.
Barium chloride is what's reacting here. That's right. And what is it reacting with?
Sodium carbonate.
Very good. Barium chloride and sodium carbonate. What are the products going to be now?
BaCO3.
What do you call that?
Barium carbonate.
Very good. Barium carbonate. And what's the other product?
Chlorine sodiide.
It's the other way around, right? The cation goes first, so it's what?
Sodium chloride.
Very good. Sodium chloride. Now, are either of those 2 precipitates? Are either of those 2 solid?
Yes.
Which one?
Is barium carbonate.
Very good. Barium carbonate is going to be a precipitate. Excellent. How about this one here? We got sodium phosphate and mercury nitrate. Now, what are our products going to be?
Is gonna be Hg.
Mercury.
Yeah, mercury and phosphate.
Mercury phosphate. Good. And what's the other product?
Sodium. Nitrate.
Very good.
Nitrate.
Sodium nitrate. Are either of those precipitates?
Yes.
Which one?
PO4.
That's right. Mercury phosphate is going to be a precipitate. Excellent. Last one here, I think, or maybe one more. What do you think about this one? What are our products? We got sodium chloride reacting with calcium nitrate. What are the products going to be?
Sodium nitrate. Chlorine, calcium chloride.
Very good. Are either of those 2 precipitates?
Number 2.
What does number 2 say?
Rule number 2 says all salts containing NH4, NO3, CiO4, ClO3 and the other.
Yep. So that means that sodium nitrate is going to be what? Insoluble or soluble?
Insoluble.
No.
No, soluble.
Soluble. Very good. So what about the calcium chloride?
That's gonna be a precipitate.
What?
Wait, 1 second. Gonna check. Number 3. It says all of them with chlorine are soluble.
Okay. So what that means is this reaction is not going to be a reaction. If I combine sodium chloride with calcium nitrate, nothing happens. Nothing happens. And that's because if we think about the net ionic equation, or the ionic equation first, you'd have sodium ions combining with chloride ions, combining with calcium ions, combining with 2 nitrate ions, and the product would be the calcium ion, 2 chloride ions. I guess I'm going to need 2 sodiums and 2 calciums to balance the equation. 2 chloride ions, 2 sodium ions, and what's last? 2 nitrate ions. So the result is nothing is a solid or a precipitate, and everything is just spectating. Nobody actually does any chemistry. So there's no reaction that occurs there. Okay, very good. Here's one that we'll let the folks at home do. You can try to find out what the solid product for this reaction is. Push pause and take a second. And all right, 1, 2. I'm going to show the answer now. So the answer is A. The calcium comes together with the carbonate and forms an insoluble product. Very good. We can also predict reactions that are acid-base neutralization or acid-base reactions. And in these reactions, if it's a strong base with a strong acid, the result is water and some other salt from the remaining counter ions. In a weak acid, weak base, or if a strong acid and a weak base, or a strong base and a weak acid, then we'll end up with a weak electrolyte, such as NH4Cl. So here, chemistry does occur because in the ionic equation, NH3 is a weak base. It doesn't dissociate, but here it becomes NH4 ion once it's dissociated. Let's show the ionic equation for this reaction here. HCl, right? Here, let's actually start from scratch. HCl combining with NH3 to form NH4Cl. If I show the ionic reaction, HCl is a strong acid because it's in our list of strong acids, so it completely dissociates. NH3 is not a strong acid, so it's just like it is. NH4Cl, that is ammonium chloride. It's an ionic compound. We can look at our list of solubility rules and see that it is completely soluble. So it'll be NH4 and Cl minus, right? And then in the net ionic equation, the chloride ions are the spectators, and so you have hydrogen ion coming together with NH3 to form NH4 plus. So this is a chemical reaction because the net ionic equation exists, right? Okay, so let's look at some practices with this kind. Well, we already did this. Let's see, that slide got out of place. Here's a which of the following is not a product of this reaction? So if I have NH3, which is a weak base, all right, and it's combining with HCN, do you know what kind of a compound HCN is?
H.
Here's a hint. It starts with a hydrogen ion. What's that?
A base.
It's an acid. Very good. NH3 is our base and H is our acid. So when these come together, what's going to happen is the hydrogen ion of an acid will always go to the base. And so you get NH4 with a positive charge and Cn minus, the cyanide ion. Okay? So which one is not a product of this reaction?
It is the top one.
That's right, NH3CN. NH3CN. So how did we know that this is how the reaction occurred? Well, because HCN is an acid, therefore it gives up the hydrogen ion, and NH3 is a base, that means it takes the hydrogen ion. And if NH3 takes a hydrogen ion, it forms NH4+. So that's what a weak base does. It takes a hydrogen ion from an acid. Okay, very good. Which of the following is the net ionic equation for this reaction? And this is a good one for people to do at home. So I'll give you guys a chance to do it, and then we'll talk about it, okay? So push pause. Make sure you have a chance to do it. All right. Hopefully you had a chance to do it. Now let's look at the answer. Okay, so we have NaOH plus HF, right? And our products here are, can you tell me what our products are?
NaOH2.
No. The Na trades places and now goes with the F, right?
Oh, F.
And what's left?
Oh, water.
Water. That's right. Very good. So now, if this is our equation, can we break it into our ionic equation?
Yeah.
Sodium hydroxide, that is a soluble compound. So this is going to be the sodium ion and the hydroxide ion. HF, is that a strong acid? Should that break up?
No.
It's not a strong acid. That's right. Your list of strong acids. Remember, the strong acids are HCl, HBr, HI, H2SO4, HNO3, HClO4, and HClO3. Those are our strong acids. Okay, so HF is not a strong acid. It stays associated for the most part. NaF, does it dissociate?
Yes.
It does, that's right. All compounds that contain sodium dissociate. Very good. And water does not dissociate. It's a molecular compound. So now, can we look for any spectator ions? Are there any spectator ions in there?
F.
F?
Yeah.
No, it's not spectating. See, it's here, it's associated with the hydrogen, and here it's separate, right? Can you see that, the change there?
Yeah.
Any other spectator ions?
Oh. Sodium.
That's right. Sodium ion is a spectator ion. So that's why the answer to this problem is C, hydroxide ion plus hydrofluoric acid yielding water and the fluoride ion. Very good. Now, this is our slide that talks about our gas-forming reactions. We're not going to talk much about these other than when a product is either H2CO3, carbonic acid, or ammonium hydroxide, NH4OH, or H2SO3, which is sulfurous acid, then those three compounds break down into gases. And when you see those kind of compounds in the products, you have to know that it's a gas-forming reaction. And that just takes a little bit of time or memorization. And because I'm not a fan of memorization, we're just going to, there's not a lot of problems that are going to be associated with this. But you do want to recognize that some compounds, not just these three, others as well, will actually break into gaseous, or decompose into gaseous compounds, which will leave the solution. All right, so we can get precipitation, neutralization. All right, so in the last little bit of this this video, we're going to talk about talk about concentration, molar concentration specifically. And molar concentration means the moles of solute per liter of solution. Okay, so when I have a solution that I've made, if I make a solution by adding, and we talked about these terms a while back, so we might have forgotten them already, but if I have a solution which is made from, remember, the pile of material is called the solute, and the water down here is called, do you remember what it's called?
Solvent.
Yeah, the solvent. The solute is the powder, and the solvent is the water. And the mixture, do you remember what you called the mixture?
Call it the
solution.
solution.
Yeah. And when we express concentration of a solution, we express it usually in science and in chemistry class. And in chemistry, the best way to express concentration is in terms of moles of solute per liter of solution. Moles of solute per liter of solution. And when we do this, we can say that that concentration, or that value, the moles of solute per liter of solution, is the molarity of the solution. Molarity. So molarity, abbreviated big M, there we are, big M, that means molarity, and it is moles of solute per liter of solution. Moles of solute per liter of solution. So if, for example, I say I have a 6 molar HCl solution, that's 6 moles of HCl per liter. All right? And if I know how many grams of a salt that I put into a certain volume of liquid, then I can identify what the molarity is using our dimensional analysis. So for example, if I want to answer this question and find the molarity of the solution, molarity, that is moles per liter. So to the right of the equal sign, I say moles, and I want to put KNO3 per liter of solution. Now, I use my dimensional analysis to try to get my moles of KNO3 over liters of solution. They're starting me with the 10.2 grams of KNO3, but I can convert that grams to moles and get the moles on top. Can you see that? So I go grams of KNO3 down here and go to moles of KNO3 here. All right. They told me down here at the very bottom there's 101 grams per mole. All right. Now I have moles of KNO3 on top, and I just need to get liters of solution on the bottom, and I can put that here. I can say I have 350 milliliters of solution, and I can convert that milliliters of solution to liters of solution by using 1,000 milliliters for every 1 liter. Very good. So using my dimensional analysis, I can solve for the molarity, which is moles of my solute per liter of solution. Now some people say, well, what needs to go here? You don't need to have something there when you're using dimensional analysis. If you can just bring in new units, especially when you need to have 2 units in the answers, mole per liter, right? So then we just go 10.2 divided by 101 divided by 350 times 1,000, and that will be our molarity of 0.2885 moles per liter, or 0.29 molar. Okay, very good. So what we are introducing to us now is a way of keeping track of the concentration, or way of expressing concentration of a solute per liter of solution. And the method is what we call molarity. Okay, see you next time. Bye-bye.